Hello everyone, welcome to the Spintangle. Today we will discuss about some interesting and also important parameters of statistical mechanics. First of all, let's write the topics today we will be discussing on. The topics are: what are extrinsic variables? What are intrinsic variables? Then a very important topic of quantum mechanics of statistical mechanics is macrostate and microstate. Okay, then we will move on to the most probable microstates. Most probable macrostates, and so on and so on. These are the main topics of today's lecture. Okay, so let's start with extrinsic variables. Extrinsic variables. In statistical mechanics and also in thermal physics, there are two types of variables depending on the internal arrangements of the system. Therefore, what we can say that the definition of the extrinsic variables are: first, make a systematic note, okay, from which you can revise each of these topics before your exam. Okay, that's why I am writing these in language. Okay, in thermodynamic limit, if a property of system depends on the size of the system, okay, if a property of the system or property, you can replace this property by variables. Okay, if a variable of a system depends on the size of the system, then it is called extrinsic. You can write it in your own language. Okay, extrinsic variable or property This means what? The basic examples of extrinsic variables are number of particles in a system, volume in a system, energy of a system, entropy of a system, and so on and so on. These are the extrinsic variables because these are the properties which are dependent on the size of the system. This means if I want to increase the size of the system, then what I have to do? I need to increase the volume of the system. What we indicate by defining the volume of a system is that the capacity of carrying particles in this box. Okay, if you want to increase the size of the box, then what you have to do, either you have to increase directly the volume, okay, directly the volume, or you can, what you can do, that you can increase the number of the particles inside the box. Okay, if you increase the number of the particles inside the box, then the volume of the box will be automatically increased. This means and the type of the wall of the box has to be extensible. Okay, has to be extensible, that you can expand, the box, and the box will look like this inflated box. Okay, if you say, if you have a balloon. Okay, if you have a balloon, and what you can do from this, you can pour it by air. Okay, you can pour it by air, and the balloon starts expanding. This means there are two things that are increasing, that the number of particles are increasing by the air you are producing. Okay, and the volume of the system is also increasing. This, and also you can see one thing, that the wall of the balloon is expandable, wall of the volume is expandable. Okay, if this does not, then there will be no volume expansion, but uh, there can uh, there can expand a number of particles up to a limit. Okay, the number of particles can extend up to a limit. So from this, what we can conclude, that if the number of particle increases, the volume will also be increased. Okay, if the walls are not so much rigid. Okay, and similarly, in this way, the energy of the system will increase, and entropy all will increase. Entropy increase means what? What is entropy? From the second law of thermodynamics, we know entropy is the degree of disorderedness. Okay, this is an important parameter, and the degree of disorderedness means how much the system goes disordered from its previous step. Say 5 minutes ago, the system was in a state, and after 5 minutes, the system undergoes a change, and its particle look like this. Say initially the system was in this state, and finally the system is in this state. Therefore, we can say that the entropy of the system increased. This is the basic concept of entropy. In some book, you can see one thing, that if the entropy increased, entropy of the universe increases if the time increases. Okay, if the time increases. This is the basic concept of entropy, and that's why one thing is related as the arrow of time, whatever it is called, the arrow of time, a new concept, one of the newer concepts of physics, and not a solved mystery of physics. This is now this is a unsolved mystery of physics, that an arrow of time is indicated by the entropy of the system. Okay, these are the extrinsic variables. What are the intrinsic variables? Now, intrinsic variables. In thermodynamic limit, if a property of a system is independent of the size, is independent of the size of the system. Then this is called intrinsic variable or intrinsic property. Say what is the number density? Say number density. An example. This is a basic example of intrinsic variables. Number density. What is number density? Number density means it is written as small and sometimes it is written as eta. Okay. Most of the books write it like n. What is number density? Number density is the number of particles per unit volume. This means if you increase the number of particles by a factor of say 2, if say giving an example, say initially the number of particles in a system was 2 and the volume of the system is V, and finally the number of particles goes increased, okay, goes increased by a factor of 2. That means the number of particles got doubled. This means, as I have told in the previous section, that if number of particles increase, then the volume will also be increased. Okay, this means what? If the number of particles increase by a factor of 2, then the volume will also increase by a factor of 2. From this section you can see that number density becomes n by V, and from the final section you can see the number density will also be become 2n by, sorry, this is 2V, 2n by 2V. This means n by V. What is this n by V? N by V means the initial number density. This means number density does not change with the system size. Okay, as now the system size becomes 2V. 2V is the system size, the volume of the system at this time. Okay, this means the number density does not changes. The number of particles can change. Therefore the mass of the system will also change. The volume will change, but there will be no increment in the number density of the particles. Okay, another example, writing it, you can check it by your own. Okay, number density, another example, sorry, what happened? Okay. Example, sir, other example, sir. Number density was the first example of intrinsic variable. You can write temperature of a system, pressure of a system. Okay, temperature, pressure, these are the intrinsic variables of a system. Number density region like small n, temperature is capital T, this is capital P. Okay, and so on. Please read the book. With these notes, please read the book, Reef book. You can read the Reef book, Reef Statistical Mechanics. Okay. Reef Stat. Reef. You can buy it, or the PDFs are available. You can ping me on Telegram. I will provide you the PDF. Okay. In the description box, the link, the number of the Telegram is given, and also the group is mentioned. Okay, you can join the Telegram group. Okay, now the two things that are very important are called as microstate. Sorry, first of all, I am writing a macrostate of a system. What are the macrostates of a system? Macrostates, say a system is maintained, as a pressure, volume and temperature. Okay, a system is given, the basic variables are PVT. Okay, you have learned in your childhood that Boyle's law and Charles' law, the basic formula of Boyle's law, the combined formula of Boyle's law is PV upon T is equals to PV constant equals to constant. Okay. There are three properties, that P, V, and T. These are the three properties that are usually used to define a system. This means, say you have a system. You have a system of gases. You have a system of gases. You can have a system in temperature PVT, and the system undergoes a change. The system undergoes a change. This means now the system becomes, say, the volume increased, therefore the pressure will be lowered. Okay, pressure will be lowered. This means temperature will also be lowered if there are adiabatic walls. Okay, say now the pressure of the system becomes, say, P prime, V prime, and D prime. The system does not changes. The system remains unchanged. The system. We will say the system remains unchanged. Not not writing this. The system remains system. Not the system is what? The system is this box and the gas. This box and the gas. Okay, this box plus gas. Okay, this does not changes in this position. But what changes, that the PVT defined the initial macrostate. Initial macrostate. And the final macrostate is what? P prime, V prime, T prime. These are the final macrostate of the system. So a system can go through various macrostates. Okay, various macrostates. These are called the macrostate is defined as PVT or NVT. You can define a macrostate as NVT. This NVT can goes through a change. Okay, and also it gives that N prime, V prime, T prime. These are the and these also can change as N double prime, V double prime, T double prime. These are the various macrostate of a system. Okay. So what we can say here, a system can have many macrostates. What another? Let me take another example. That, say, this is a hotel room. This is what? This is a hotel room. The room remains unchanged, but say it is maintained at pressure, volume, temperature, or number of particles, NVT at something, and someday, say this is on 5th August, and the room will be changed on 7th August. On 7th August, the 7th August, what will be NVT? NVT will be different. That will become N prime, V prime, and T prime. Okay, this means the room and the system, and room and the environment is the system. The system does not changes here. The room remains room, but what changes? The situation of the room. The situation of the room changes. This is called, the system is in initial microstate. Say this is microstate 1. It is read as microstate 1. The system is in. Read it like this: the system is in microstate 1, and here the system is in microstate. Sorry, this is not microstate. This is macrostate. Macrostate 1. The system is in macrostate. Okay. System is in macrostate 2, and the day passes by. The system will changes, and also the macrostates undergoes a change. Okay. Say another example. Let me take another example. I will make it clear to you. Say a box, a ice cube. Say a ice cube. Say ice cube has temperature something, say ice cube has temperature T. Initially the ice cube has a temperature T when it is draw out of an deep freezer. Okay, initially this is initial temperature, and the ice cube changes its temperature as the time goes. Okay, as the time goes, the okay the ice cube changes its temperature. The temperature loss is gradual. Okay, the temperature loss is gradual here. So this is not discrete, I'm just telling it, but this is gradual, or this is a systematic. This is a systematic, and each point of the system and each microsecond after the system changes its temperature. That means this is the macrostate 1, this is the macrostate 2. Sometimes macrostate is written as capital M and microstate is written as small m. Okay, these are the macrostate the system will go through. Okay, this is the macrostate of a system. It is, I think it is clear to you. If it is not clear, then comment on the comment box. Okay, then what is microstate? Very important topic is microstate. The first let me write the definition. Change the English. The various internal arrangement in a system in a particular, I am writing it from the book. Okay, writing it from the book. Particular macrostate is known as microstate. Sorry, microstate of the system. Say one thing that let me take an example. Say a box carries three particles. Carries three particles. The red particle is here. The blue particle is here. Say the sky particle. Okay, and the green particle is here. This is what? This is a macrostate. This is a macrostate. A macrostate is defined as a microstate is always remains inside the macrostate. This is a macrostate. A macrostate is defined, initially the macrostate is defined as three particles in three boxes. This is the definition of the macrostate. This is the definition of the macrostate. Now, this is the red ball in the box 1, the blue ball in the box 2, the green ball in the box 3 is an arrangement of microstate. Then what we can conclude from this? We can say let me change the ink. This is, I have to take it very much carefully. Say this is the box after some time, and these are the compartments. What are the compartments? The compartments are labeled as 1, 2 and 3, but the red ball goes here, the blue ball goes here, and the green ball remains on the same place. This is an arrangement of macrostates. Okay, this is an arrangement of the microstate. These are the in this place, in the first place, what we can say, that the red ball is in the state 1, the blue ball is in the state 2, the green ball is in the state 3. But in this arrangement, what we can say, the red ball is in the box 2, the blue ball is in the box 1, the green ball is in the box 3. You can see from from this figure that the macrostate does not changes here. The macrostate does not changes here, but the arrangement of microstates changes here. These are the arrangement of microstates. These are from the definition you can see that the various internal arrangement. These are the internal arrangements. Okay, the red ball goes on the box 2. The blue ball comes in the box 1. But the macrostate remains same. The macrostate was defined as 3 particle 3 boxes. This is also 3 particle 3 boxes. The macrostate does not go and undergoes a change. Okay, 3 particles and 3 boxes. This is the macrostate, but the microstate is changed. Okay, this is another arrangement. This is another microstate. This one is say microstate 1. Microstate is written as small m. This one is microstate 2 because the arrangement has changed here. And in the third example, in the third case, you can say what is this? Say this is the box. These are the compartments. Say the red ball goes here. Red ball goes here. The green ball comes here, and the blue ball is in the middle compartment. This one is the 1, 2, 3 compartment. Okay. This means the red goes in the 3, the blue goes in the 2, the green goes in the 1. This is another microstate. This is say this is microstate 3. The macrostate does not changes here also. The 3 particle 3 box macrostate does not changes here, but the microstate undergoes a change. Okay, the microstate changes. These are the individual microstates. This is very important for distributions, for various kind of distributions in bosonic fermionic systems. Okay, and also Maxwell-Boltzmann system. We will discuss it. Maxwell-Boltzmann, bosonic and fermionic systems. If you do not know what how the distribution works, then you will not be able to do problems related to these. You will be asked say a question. You will be asked to arrange. You will be asked to arrange 3 particles in two boxes. How many ways? In case of probability, in lecture 1, I think so, lecture 1 and 2 was for probability. I think you are not unknown about the probability distribution. These are the probability distributions. Okay. In case of this will slightly changes the 3 particles in 2 boxes. The particle will be distributed. Then how many ways are there? If the particles are distinguishable, if they indistinguishable, then they will be distributed regarding the fact that whether the particle is distinguishable or indistinguishable. Okay. This was a type of question. So what we can say, the number of microstate, the number of this is the question. Okay, let me remove the question first. For a systematic note, let me remove the question. You can write it in your copy. Number of microstates are very large for a system. Number of microstates are very large for a system. Some people say that some students, I have seen that some students says that these particles, that internal particles, they call the internal particles as microstates. This is a wrong concept. These are not the microstate. and they say that the complete thing is called a macrostate. Okay, the macrostate is correct, but in case of the concept of microstate, the concept is incorrect. The microstate are the internal arrangements. This means if the particle, they say this is a bigger particle, these are the smaller particles. If the particle goes here and this particle goes here, the microstate will change. The microstate will change. Okay, this thing you have to remember, this thing, that the microstate is not always not the particles itself. It is the internal arrangement of the particles. Okay. Now let me go to the next topic. Sorry. The next topic is most probable microstates. What are the most probable microstates? Let me make an example and say an example. Say from your school, say class 5 students, from a school class 5 students, this is the macrostates. Say these are the macrostates. Macrostates are what? Macrostates are, say class 5 is a macrostate. And what are the microstates? Microstates are, say class 5 has this is not the right thing to write. Say class 5 has, I'm just telling it. The class 5 has 500 students. 500 students. This is not macrostate. Let me remove this. Sorry. Say this is class 5 has 500 students. This is class and this is students. Say class 6 has 600 students. Class 7 has 1200 students, say, and class 8 has, say, this is 400 students. Okay, this is okay. So what are the total number of students here? 1600, 2200, 2700. 27, the total number 2700 is the total number of the students. Okay, first understand this thing and then write it in your copy. 2700 is the total number of students in a school, in the school. So what is the probability of getting each students? This is, what is the probability? The probability of choosing one student is 1/2700. Okay, the probability will be what? 1/27. This is the basic probability. Now you can easily see that the probability of choosing, I am writing like this, the probability of choosing class 5 student a student from class 5, a student of class 5, what will be this? Single particle probability means single probability is what? 1 upon 2700. As there is 500 students, then what will be here? There will be 500 times 27. How does it comes? You can easily see that this is a OR relation. This is a OR relation. Why OR? If someone comes into the class and want to choose a student, then he will choose roll number 1, or he will choose roll number 2, or he will choose roll number 3. This means this is a OR relation. Okay, OR relation. In case of OR relation, the probability goes summed up. This means 2700 plus 2700 plus 27 up to 500 students in case of class 5. Have you understood? This is a OR relation. This is a OR relation. Why OR relation? Either someone want to choose the roll number 1, or either he will choose roll number 2, roll number 3, roll number 4. These are OR. If he choose roll number 1, then he will not choose roll number 2. This means either an OR relation. These are the English terminology, I think so. Probability of a student of class 7, I am not writing this, you can write it in your copy. Student of class 6. Class 6 student, how much was the class 6 student? 600, 1200, 400. Okay. In this case, it will be 600 times probability of each student, 2700. Probability of class, this is class 6, this is class 7. 7 is what? 7 is 1200 times 2700. And probability of choosing a student of class 8 is what? Class 8. This is class 8. Is what? 400, I think so. 400 students. 400 students times each student probability. Okay. This comes from the summing property. Okay. This means what is the probability of, this means the probability of taking, we can easily see from this fact that, let me change the ink. This probability is the maximum because this is 1200 times 2700. This is the maximum probability. This means probability of taking a student from class 7. I am writing it in easier way. Okay. Probability of 7 student is the maximum probability. Then what comes? Then comes probability of choosing a student from class 6. Then comes the probability of choosing a student from class 5, and then comes the probability of choosing a student from class 8. This is most interesting. This means the maximum probability, if the this means this is the one thing, the most probable, this is the most probable macrostate. Okay, the most probable class is class 7. What was class 7? Class 7 is the most probable class. Okay, in this. Now, writing in statistical notation. Okay, say microstates. These are the microstates. Sorry, these are the macrostates. Write macrostates here. These are the macrostate, and then in this side, these are the microstates. Say a system A has microstate 100. Okay. The system B has number of microstates. Microstates are the arrangements, I have said it earlier. And C has number of microstate as 800. Then what will be the most probable? The probability of choosing a microstate from macrostate C is greater than. PC, probability of C is greater than probability of B is greater than probability of probability of A. Probability of A. You can easily resemble this thing with the previous example. Okay, with the previous example. This means what is the most probable? Most probable macrostate is which? Most probable macrostate is the macrostate C. Here comes the macrostate C. Okay, I think this will be clear to you. Now, what we can conclude? Let's conclude. The macrostate having largest number of microstates is called most probable macrostate. I think, is it clear? In this case, in the previous case, what is the most probable? Most probable macrostate was what? Was the C macrostate was in case of most probable macrostate. Most probable macrostate is, see, I am writing it in short because I am too much a lazy person. Okay. So this was the most probable macrostate. In the next lecture, we will also discuss about most probable macrostates and a topic called entropy. Okay. Most probable further discussion on most probable macrostate will be discussed on that fact, and I have to make a separate video on this. Okay. So wait for thing, and I am telling you this lecture is a part 1 part 2 lecture. Most probable part 1 part 2 lecture, and I will provide a part 2 lecture also from this topic. Okay, very soon. Today I will upload it on 6:30 p.m. and also the later lecture will be uploaded on around 9 p.m. Say this is 9 p.m. It is not recorded. I will record it. Okay. Okay. Thank you for staying with us.